Okay, good morning, everybody. So we're going to continue on with our look at spatial statistics. So last time we're looking at clustering, looking at different tests to quantify clustering, things like Moore and Xi, what we looked at in this week's lab. Now we're going to get into the second part of spatial stats, which is spatial interpolation. Basically, how can we determine unknown points between observations that we have of some variable across the Earth's surface. Okay, so like clustering, right, we're still adhering to Tobler's law of geography that most things are related, especially things that are closer together. But instead of analyzing and trying to quantify patterns or clustering of some variable in space, with interpolation, we're trying to model or guess or predict what a certain value of a variable is going to be based on known observed variables that we do have that are discontinuous in space. We're basically trying to fill in the gaps of what the variable values that we do not have. Right, so basically we're taking a bunch of sample points that we do have a measurement of some variable, and we're trying to guess or determine what the number or the value of the variable is going to be between those points. So there's a bunch of different ways that we can go about this, and that's what we're going to talk about first of all in this lecture. And so spatial interpolation has mostly to do with modeling or predicting what a surface is going to be. Now, that surface can be elevation, it can be voter intention, it could be temperature, it could be human, it can be physical, right? But we're trying to guess what the unknown values are between known values. This is the essence of spatial interpolation. So spatial interpolation, right, it's a very common geostatistic technique used a lot in different fields, right? Hydrology, water science, so trying to predict unknown values of precipitation based on known values. It was originally, a lot of it was developed for mining, trying to figure out where certain variables or finds would be based on known data of soil, mineral composition, things like that. But it's applied across a whole bunch of different physical and human related aspects of geography. So the essence of spatial interpolation is this. We have a series of sample points indicated by the crosses here. And basically what we're trying to do is determine or calculate what the unknown, what the value of that variable is at the unknown point. And then once we calculate that, we can create a relatively continuous surface, right? So a common example is elevation. We can create a elevation map like this, a digital elevation map, based on interpolating between known values to fill in the gaps to give us a relatively continuous variable of elevation. So where we apply spatial interpolation, we're dealing mostly with interval or ratio, right? We're not looking at nominal or ordinal data in this case. We're applying spatial interpolation to continuous data, data that has value along a scale. So it's interval or ratio data that we're going to be using to spatially interpolate some variable. Right, so again, the rationale or the kind of the theoretical underpinning of spatial interpolation is that we're following Tobler's law of geography. Things that are closer together tend to have the same value, not always, but that's kind of the underlying assumption when we're doing spatial interpolation. Things that are closer together tend to have similar variables, and therefore we can predict based on the distance of some known variable, so known value, what the unknown value at another location is going to be. And again, spatial interpolation, right, it's found in basically all your ArcGIS and your general geographic information system applications. Should be able to perform this. So again, imagine we have some point data here. Now this point data can be anything. And essentially what we're going to do is convert this point data to a grid data or a surface. So right, 14 goes to 14, 20 goes to 20, 27 becomes the grid square of 27. And then from all those known values, you can see that we've filled in what the unknown values within this simple surface is going to be. So basically we're taking point values and converting them into continuous variables. And like I said, this is done in numerous fields, right? Elevation, rainfall, because we only have a limited number of real observations, we have to guess what the missing values between all of the known points is going to be. And once we do that, we can convert that discrete or discontinuous data set into a more continuous data set. Of course, there is uncertainty because we do not know what the values, of course, are between the known observed values, but we can use different techniques of interpolation to get a better idea of what the likely value between two known points is going to be. So a common one, right, in hydrology, that's what I study, is in spatially interpreting values like precipitation, because we only have a certain number of point measurements, rain gauges, snow gauges, things like that, that actually give us an idea of the actual amount of precipitation that's fallen, say, over the last day, right? We have to interpolate, right? So all of these numbers here and all these points are different values, right, of precipitation. And we take those known values and we can make a continuous map here, which gives us a better idea of the general variability of precipitation in this case. So how do we go about doing spatial interpolation? Well, there's two basic types of spatial interpolation methods. One's called deterministic interpolation. So a couple examples we'll go over is called the inverse distance weighting and the spline. And deterministic means that it's based on, the interpolation is based directly based on the observations, okay? And then we have a more sophisticated approach to spatial interpolation, which is called geostatistical interpolation methods, where we're looking more at how the values vary across space, right? Remember, like things like autocorrelation, to get a better idea of how variables likely differ between known values. So we're going to look at a couple examples of geostatistical interpolation methods, which is trend and kriging. Right? So again, all these different methods, whether they be deterministic or geospatial types, are going to give us slightly different maps of what the variable is going to look like. So again, in this case, we're taking the variable in the top left here. Those are the station observations. Maybe this is temperature or maybe precipitation. And you can see that the interpolation methods, the three different ones we're looking at, the different squares there, give us similar but slightly different maps of how that variable likely varies across all of that continuous distance. So the first one I'm going to look at is the deterministic method of inverse distance weighting, IDW. So the essence of IDW is that it takes a series of points, observations around the location that you're trying to predict or model, and it assigns the value based on the values around it, but also the distance that those points, those observed points, are from the point that you're trying to interpolate. So how you define where, so imagine down here in this right here, we have a point right there that we're trying to interpolate based on the red points, the 5 red points around it. How many points that we're going to take into consideration is going to be defined in IDW by the search radius. So this limits the number of observed points that we're going to use to determine the interpolated value. So there's a couple of different ways we can set the search radius. One is a defined distance away from the point we're trying to interpolate. Maybe it's 10 meters, maybe it's a kilometer. It's going to depend on our observations and our scale. And another way we can set our search radius is by a certain number of points. Maybe we're going to set, say in this case in here, we're going to set our minimum number of points to be 5. So we need at least 5 points, right, in order to use those points to determine what the unknown value at that location is going to be. All right, so example here. So we have a set number of points and we're trying to interpolate what is going to be the value at the star right there where the arrow is pointing to. So in this case, we're going to give the greatest weight or the most influence to the value of 34.6 because it's closer to the star, the unknown point, right? This is what essentially what inverse distance weighting means that the closer that the observed point is to your point that you're trying to predict, it's given more influence. And for example, the furthest point is going to give the least weight. And then all the other points in between those two are going to have an intermediate amount of weight in determining what the interpolated value at the star is going to be. Okay, so that's inverse distance weighting, kind of the most straightforward way to undergo spatial interpolation. Another way another deterministic approach is what's known as a spline. So spline is somewhat similar, but it tries to fit a best fit surface through a set of known observed points. So this might be anything: pollution concentrations, water table height, elevation. So imagine you have a series of observations of water table heights that you have across an area. You could use a spline curve to basically fit a surface, which would give you a guess of what the water table heights are going to be at points in between your observations. And the way that you can modify your spline curve is by adjusting the tension, which basically changes how well the surface is going to fit through your observed set of points. So an example here, we have 1, 2, 3, 4, 5, 6 points right there. And that blue and orange line is basically our spline curve, which basically smooths out. It's kind of like a best fit line, but a smooth line that gives us a surface based on those points. So another example here where we have these blue dots, right? Those are our observations, right? That might be elevation, that might be water table height. And then basically we're using a spline interpolation to fit a line between those points to give us a continuous surface, or a continuous line in this case, between our observations. So kind of similar to the spline curve is a trend analysis, where basically we can fit a mathematical function through a given set of points to give us a surface. So in this course, we've been looking at linear regression, right? Basically using a linear mathematical formula to predict a dependent value based on a independent value. So basically we can use a mathematical function or a polynomial, right? So a linear function is a type of polynomial, and we fit the line and create the mathematical function based on something like a lowest residuals or least squares approach that we looked at in regression. So we have polynomial, right? Meaning basically many terms, right? So we can have very simple polynomials, right? With linear functions, we had a first degree polynomial, but we can have a bunch of different more complicated polynomials where we have a quadratic or a cubic or a quadric or a quintic fifth degree polynomial, where basically we have more terms added to the mathematical function. So example here, imagine I have a set of points of y value over a horizontal distance of x. These are my points in the blue diamonds right here. If I wanted to try to model or interpolate those points using a linear regression, right there, a linear function or a linear polynomial, it's a very simple mathematical formula, but you can see that it does a very poor job at describing or basically going along those observations. So I could increase the polynomial to a fourth order polynomial. So now you can see that the mathematical function describing y based on x is much more complicated, right? Fourth order, meaning we have an x to the fourth, followed by an x to the 3, x squared, x, and an intercept. So you can see that we get a much better description of our observed values. There's still some discrepancy between our line surface, interpolated surface, and our values, but you can see that the fourth order polynomial does a much better job at describing that complicated surface. Okay, so another geostatistical approach to spatial interpolation, it's what's known as kriging. So kriging was developed by a South African mining engineer about over 50 years ago, well over 50 years ago, probably closer to, oh, there it is, 1939. So about 80 years ago. So he developed kriging as a way to spatially interpret known data to try to get a better idea of where he might be able to better find gold deposits. So kriging right now, or over time, became applied, not, it came from mining, but it was applied to various other disciplines. And because it's essentially just a tool of geostats. So the essence of kriging is that fundamentally it's kind of like inverse distance weighting in that you usually give more influence to closer points in determining what the value of an unknown location is. But unlike inverse distance weighting, the weights are not just based on distance, but kriging also analyzes the spatial variability over distance. Basically, it looks at the degree of autocorrelation between values and also takes that into account to try to better interpolate what the value is going to be between observed points. And to do this, to basically describe the nature of autocorrelation in a data set, it uses what's known as a semi-variogram. So a semi-variogram quantifies how 2 points are related to one another spatially as the distance between those points increases. Right, so kind of like with inverse distance weighting, right? If we're looking at trying to interpolate what a value is going to be at a certain location, we're going to look at observed values surrounding it, but we're also going to apply geostatistics based on creating this semi-variogram. Sometimes it's called the variogram. All right, so the first thing in kriging, right, we got to construct our semi-variogram based on observed values of whatever the variable is that we're looking at. Gold deposits, soil moisture, elevation. So the semi-variogram essentially is made up of 2 parts. The first one is the experimental variogram, which is based on the constructed from the observed values that we actually went out and surveyed. And then from that experimental semi-variogram, we're going to create a model semi-variogram. And the model is basically fitting a line through the experimental semi-variogram. So again, when we look at a semi-variogram, it usually takes on kind of like a scatter plot form, where we have distance along the horizontal axis, and then variance on the y-axis. So basically what the semi-variogram is showing us is that how much 2 points are going to vary from one another based on how far they are from one another. That's what the semi-variogram is basically telling us. So yeah, again, kriging, the semi-variogram is the main tool used in kriging. And you can think of it as basically giving us an idea of the degree of autocorrelation between 2 points. Again, going back to the idea that the underlying assumption here is that 2 things are going to be more similar if they're located closer to one another, but the semi-variogram used in kriging gives us a better, quantifies better how much those 2 points are going to vary spatially. So if I look at the semi-variogram a little bit closer, and what it's telling us is that it basically is showing us the semi-variogram how far we have to go before the values at any 2 points have nothing to do with one another. So you can see in this semi-variogram here, we have something called the lag, right, which is the horizontal distance. Then we have this Greek letter up here, which is basically our variance, right, how much those 2 values differ. So we can see that as our distance, if we start down at the bottom origin down here, the bottom left, we can see that as our distance between 2 points increases, the variability or the variance between the 2 points increases. Makes sense, right? The further too distant, the larger the distance between 2 points, the greater the variance between them. But you can see that variance, once we get to a certain point, tapers off. Okay, so basically the semi-variogram tells us how far we have to go or what distance we need between 2 points before the value at those 2 points has nothing to do with one another. Basically, there's no more spatial autocorrelation. Right, so again, there's our variance right there. There's our horizontal distance between those 2 points. And then we have 3 other aspects of the semi-variogram there, the sill, the range, and the nugget. So again, the leg basically tells us the Euclidean distance, so the straight line distance between 2 points. And then the sill itself basically tells us the value of the leg that you need to get to, right, before you have no autocorrelation between your points. Right? So basically the CIL, right, is the value of the, as the lag tends towards infinity. So the CIL occurs at the distance of the range. So basically the range is the horizontal distance that needs to be between 2 points before you obtain the CIL. And the CIL is basically where we have no more association, autocorrelation between two variables. So again, the semi-variogram is essentially telling us how far we have to have between 2 points before they don't have anything to do with one another. Right? So again, the range, right, gives us the distance between 2 points before they have nothing to do with one another. So think of it as how far you have to go before one data point has no bearing or no influence on what the value is going to be at another point. And then the nugget, if we backtrack from the CIL and go back towards the origin, we reach the nugget. And you can see that the line in the modeled semi-variogram does not go to the origin exactly. The nugget actually describes the amount of subgrid or sub-measured spatial variability that is unknown. Okay, that's kind of like the y-intercept of the semi-variogram. Okay, talk a little bit about spatial dependency now. Something called the friction of distance. So far we've been talking about Euclidean distance, you know, the straight line distance, latitude, longitude, or coordinates between two locations. We also have something called the friction of distance. Basically, the friction of distance describes how hard it is to travel from point A to point B. Think of the difference between traveling 100 meters walking across a flat open field compared to walking up a jagged, very steep cliff, right? Both are 100 meters in length, but of course, walking up the cliff or the very steep slope is going to be much more difficult. So you're going to have a greater friction of distance, which is going to cause you to take more time to go from point A to point B. Another example is traveling a kilometer on the open road compared to traveling a kilometer in a downtown big city, right? Both are a kilometer, but of course, more traffic, more obstacles, people, pedestrians, things in the big city is going to cause you to have a greater friction of distance over that kilometer, and is going to result in you taking longer to travel that kilometer in the city compared to the open road. So the friction of distance allows us to determine how far we're willing to go to reach a certain location. And it tells us something about the interactions between two locations. The larger the friction of distance between two locations and the larger the distance itself, the less likely we're going to have interaction between those two locations. So there's a YouTube video that gives a bit deeper description of what the concept of friction of distance. So the friction of distance, right? A main component to it is what's called the distance decay model. And the distance decay model describes how the interaction between two locations decreases with distance, right? So the distance and the interaction are inversely proportional, meaning that as the distance between 2 points gets longer or larger, the interaction or how much they interact is going to decrease. But how that decrease occurs is described by the distance decay model. So of course, the shorter distance between two locations, you're going to tend to have more interaction between two locations, especially if we have a low friction of distance. But as the Euclidean distance increases and the friction of distance increases, we get a rapid decrease in how much two locations are going to interact with one another. So here's 3 basic models describing distance decay, right? So the first one on the left is just a linear distance decay model, right? So the distance is on the bottom, on the horizontal. The W is the interaction. So a straight line linear relation. As the distance increases, we have a straight line decrease in the interaction. So maybe think about noise levels, right? The further away you get from where a noise is coming from, the amount of noise that you hear is going to decrease in a fairly linear or proportional way. Second type of distance decay model here, in the middle here, B, is called a negative power distance decay. So you can see that the negative power distance decay, there's a sharp drop off in interaction with as soon as you start to move away from the location. Okay, so there's a sharp drop off initially with distance, but that drop off, right, the rate of drop off decreases with greater distance away. So it's still decreasing the whole distance that you're moving away from the point of origin, but that rate of decay slows down as the distance increases. And then similarly, the third one is a negative exponential distance decay, right, where it's kind of similar. It's not quite a linear interaction or decline or decay, but it's a semi-curved. So a good example of distance decay and different models of distance decay is the number of customers or how far you're willing to travel to go to different types of store. So imagine a convenience store, right? Most people would not be willing to travel, right, more than a couple kilometers if you live in a town or a city to a convenience store, right? They might travel a little further to a grocery store, right? And they're more likely to travel even further to a big box store like a superstore or a Costco or a Home Depot, something like that, right? So these three different types of stores, right, have different distance decay models, which describe the willingness of people or the interaction between customers coming to those stores. Right, so again, same kind of idea here. The distance they're willing to travel to a convenience store is going to drop off very sharply, right, as you get further and further away. Grocery store is kind of in the middle, and then a department store, superstore, or maybe a furniture store, that decay is going to be more slow, right, because people are more willing to travel longer distances to the departmental stores. And then we have new things like e-commerce, right, Amazon, Temu, all those different apps out there, whereas basically, right, we have the same amount of willingness because basically everything is delivered to you. So we have no distance decay in that case. So in terms of the idea of distance decay and different types of stores, right, the reason why people won't be willing to travel very far to a convenience store, right, is because usually at a convenience store, you're buying small priced items, right? Maybe a little bit of food, a snack, a little bit of gas, things like that. So no real large specialty items. And therefore, convenience stores, that's why they all tend to have basically the same kind of variety of services and products, right? Grocery store, right? Be willing to travel a little further to a grocery store based on your tastes. But, and usually you're going to a grocery store, you know, maybe once or twice a week, maybe more, maybe less, depending on, you know, your personal circumstances. But usually you're going to buy more at a grocery store and your purchase is going to be higher. So usually you're willing to travel a little further to a grocery store compared to a convenience store. And then on the extreme end, where you have a big box store, departmental store, this is usually where you're going to make a large, high-priced purchase. Maybe an appliance, refrigerator, sofa, television, something like that. Something that you do not purchase very often, not like a convenience store or a grocery store. So you're willing to travel further to make that purchase. Maybe you see a deal on in the next town. You're willing to travel maybe an hour, maybe two. A lot of people do it all the time, going down to Costco in order to buy larger quantities of higher price items. And so this is basically the idea of why different types of stores, these three different types of stores, generally have different distance decay models. Okay, so we'll talk a little bit about geographic data. And geographic data, unlike other regular types of data, is unique because, of course, with geographic data, not only are we describing the spatial locations, maybe by a coordinate or something like that, but often associated with that spatial location, we have some non-spatial attribute or characteristic coming along with that. So geographic space is continuous, right? We just talked about different ways that we can try to guess what the unknown values along the continuous field is going to be. But unlike other types of data, geographic space is continuous, and we're trying to describe what a variable is going to be along that continuous space. And of course, we all know by now, right? Geospatial data is spatially dependent, right? It might be clustered, it might be negative autocorrelation, it might be random in nature. And unlike other types of data, when we're looking at geographic data or geospatial data, we can look at different variables, right? Which are represented in different layers. If any of you guys have used a GIS program, you know that you can look at different variables by looking at different layers within the GIS program. And then we use different geospatial models to try to model or guess what the real world characteristic of certain geographic objects are, distances, things like that, using different types of data model types, whether that be vector or raster data. So as geographers, we're essentially interested in trying to describe three main properties of spatial distribution. The first is density, which is essentially just the frequency or how common a certain observation is within a space. Okay. Second one is concentration. Might be, you can think of concentration in this context as clustering, right? How much spacing or how closely spaced together is the variable? Is it clustered, or are like values located further away from one another, where you might, in that case, have dispersed or regular spacing to your variable? So concentration or clustering, the degree of clustering is another one. And then the third one is pattern, to see if there's any geometric arrangement of your variable throughout space. So another thing that we do in geospatial data is geoprocessing, where we can use an online app, a computer app like ArcGIS or some other geographic information system platform to try to do a bunch of operations that allow us to better understand our data. An example of geoprocessing is putting a buffering or a guard around our data. So imagine we have a point, a line, and a polygon shown here. We can apply a buffer, put a buffer around that, basically a distance, a perimeter around it, to basically, maybe you want to make an exclusion zone. So here's an example right here. So those black points are high school locations around Los Angeles. And this person has gone in geoprocessing and put a half-mile buffer, in this case an exclusion zone, around all of those schools. Talk a little bit about the basics of geographic data now, and these are referred to as basic primitives. These are kind of the basic building blocks that we use to create geographic data. In the last lab, we looked at something used something called a shapefile, right? Which is basically a file which contains a bunch of different components, both spatial and non-spatial characteristics. Right, so first thing is place, right? With place, what we're trying to describe is maybe the shape and the size, basically the scale of the object that we're looking at. Also, we like to put names on things. So that's another way that we can describe a place, by its name. And another way you can describe a place is by where it's located on some type of coordinate system. For example, latitude and longitude, universal transverse Mercator, what have you. And then often we're looking at our data, not only two-dimensional, but sometimes three-dimensional as well, especially if we're looking at something like elevation. So other than the place, then we have the characteristic of the place called the attribute. Okay, so with each of these geographic locations in geographic information systems, our data also has an attribute associated with that place. In this week's lab, we're looking at the Nepal data, right? And we looked at all the polygons. There's 30 some polygons across Nepal. With each of those polygons, right, those geographic locations, we had different attributes, whether that be adult literacy rate in females or contraceptive use or population density. So with each of these geographic locations, we have an attribute, or usually many attributes associated with them. And these attributes can take on different types of data types, right? It can be nominal, ordinal, interval, It can also be spatially intensive measurements, like a population density or some kind of density. Remember, we talked about spatial intensive measures versus spatial extensive measures, where spatial extensive measures, the value within a geographic location has to do with the size of the geographic location that you're dealing with, right? So if you're using a GIS program like ArcGIS, right, you can open the attribute table where it'll tell you the value of all the attributes, right, that are associated with a certain spatial location. So these are basically usually put together in terms of tables. And then we can also describe a geographic location physically or visually based on points, lines, and areas, right? Through something like we looked at in the lab, like a shapefile, right? So we can describe points, lines, and areas, right? Through polygons, right? Polygons describe areas, polylines to describe a linear feature, and then representative points to describe point locations. And then, of course, with GIS, we can look at various or different variables at a certain geographic location at one time. So all of our different attributes, right, we can think of as being contained in different layers. So we can analyze the different variables or attributes one at a time, or we can overlay them to do a more complex analysis, right? We can combine the layers. And then we have in GIS and geostats, we had two basic types of data, right? Or in how they're represented. One's called the discrete object view. Now, this is usually an object that has a known or definable boundary around it. So think of like a parcel of land, a road, a lake. That lake is going to be described spatially or visually by an area or a polygon. So that lake would have a defined geographic spatial boundary drawn around it. And therefore, it would be an example of a discrete object view. Right? So other examples, buildings, road, land parcels, all have a definite boundary to where they exist, drawn around them. So you can think of a discrete object as anything that basically is like a noun, right? Building, lake, river, street, right? Basically all nouns are going to be discrete objects because they have a definite spatial border drawn around them. Right, so you can think of, right, a property map is definitely going to be an example of a discrete object data type, right? Because you can see exactly where each object begins and ends. And then the other type of data type that we look at is called fields or continuous field view. So this is basically a surface, which is basically measured in reference to another location. So in reference to another fixed point in space or from like an emitting source. So sometimes these field data is also referred to as non-discrete or surface data. So an example of a field data is elevation, right? We all know that elevation, a common way that it's expressed is MASL, right? Meters above sea level, right? So in this case, we're describing a continuous field variable, elevation, in relation to the 0 point, which is sea level. Okay, so all the elevations, right, at each of those grids or along that surface is going to be in reference to 0 or sea level. So that's the fixed point in which all of the field data or the continuous data is determined from. Another example is aspect, right? Aspect basically tells you the direction in which a sloped surface is facing, right? A north aspect versus a south aspect. So in this case, we have a variable which has a reference, usually in terms of azimuth, which is due north, which has an azimuth of 0. An azimuth of south is going to be 180. 270 is going to be an azimuth of west. So it's an example of a continuous variable because it's in relation to a reference point, a certain reference point, which in this case for aspect or azimuth is going to be true north, which has an azimuth of 0. Okay, so kind of a shorter end to today's lecture videos. So we have one more lecture video We'll wrap things off next week with regression analysis. We've touched on regression a little bit already. We'll look at some more examples of how to apply regression analysis in trying to predict unknown variables across space. But other than that, I'll shut things down for today. So everyone have a good weekend, and I'll see you for the last lab, lab 8 on Tuesday. Have a good weekend, everyone.